This is for the color code, and here I have bands of brown, green, brown, and gold. And what I'm measuring is 149 ohms. This one here is red, red, brown, gold, and I'm measuring 220 ohms. And before I forget those numbers, I will enter them. I will be able to remember the colors, but not necessarily the numbers that I'm measuring here. Okay, this one here is red, yellow, brown, and gold, and I'm measuring 242 ohms. There's always a little bit of tolerance in these resistors. And of course, the ohm meter has to measure that as well. And now I need to fiddle around here and put the fourth resistor that I want to measure. Okay, so for this one here, I have brown, black, red, and gold. I consider the gold one to be the last one of any of these. I just happen to turn this one around here. So brown, black, and red and gold. And measuring the resistance, and I come up with 992 ohms. And as far as measuring is concerned, that's all I need to do here for the color code.
This is going to be a very quick recording on the color code, how to analyze the data. These are the resistors that I used, and these are the colors I came up with. And trying to analyze these here is looking at these numbers that I measured. And keep in mind, these are measured numbers. These are very close to the numbers that the resistors are rated for, but they're not exactly on it. So it may be 150 perhaps. This one here may be 240. This here may be 990 or perhaps 1000. There's a little bit of tolerance in there, which, by the way, I should give away. That's what the gold means. I don't think you would be able to figure that out just by looking at the resistors. The gold, so I have to give this away. The gold means that there is a 5% tolerance for resistors. So you could have something 1000 ohms plus minus 5%, which is plus minus 50 ohms. Okay, let's look at the colors here, the other colors. And I would say that kind of looks like this one here with the red, and then it says 220. Perhaps red means 2, and we can see that here 2 as well. There's a 2 there for red. Sure, there's a 2 here as well, but there may just not be enough space here to accommodate this 2, besides that this one is a measurement and it should be a rounded number to, well, perhaps 240, and that 2 really doesn't mean much. But this one here seems to mean something, the 200 here and the 220 here. So perhaps 2 means red. Well, if 2 means red, then perhaps 1 means brown. And then the brown appearing here in the third color band perhaps has something to do with these numbers being in the hundreds. And this number here, even though it does say 992, which is in the hundreds, admittedly, but remember there's some tolerance. Maybe that's 1000, actually. And then the red means perhaps that this number is in the thousands. So it would also have some kind of meaning, the 2 over the 1 here in the third color band. But as I said, this is going to be really quick, because if I go on here with any more, I would take too much away from your work. Figuring out the color code, after all, you will see, is really not that hard.
This is the circuit with just one resistor. I'm going to use a 1000 ohm resistor, unlike the one that is listed on your lab sheet, because I don't want to take work away from students. Okay, there we go. Okay, I'm going to connect this here with a switch, because I will at times have need for turning off the switch, such as I start out. According to the color code, this is a 1000 ohm resistor, and now I'm going to measure the resistance. And so I turn my multimeter. You're likely to have a different multimeter. So I turn this one here to ohms, and within the range that I'm supposed to measure. And the way I measure it is two things. One is I go from the outside, so parallel. I go in here and measure the resistance, and it comes out to 992 ohms. The other thing I have to pay attention to is that it's not part of a circuit. In fact, right now it's not. With the switch being in the off position, it's not part of the circuit. As soon as I connect it with a battery, I cannot measure the resistance anymore. So it has to be outside of a circuit. So again, 992 or 991. There's a little bit of tolerance in there. I'm going to write down the 992 ohms. Then I'm going to close the circuit, and I'm going to measure what voltage I have. For that, I have to turn this one to volts, and I come up with 3.24 volts. I don't pay attention to the negative. That just means that my leads are the opposite way. There we go again, 3.25 or 3.24 volts. I'm going to go with the 3.24 volts. Again, there's a little bit of a tolerance in there. And then I measure the current. Oh, by the way, for the voltage, you may have noticed I measure it in the same way as I measure resistance, from the outside parallel to the resistor. In this case, of course, I need to have the battery hooked up in order to have a closed circuit, in order to measure voltage. Okay, for amps, I turn this one here to amps. Knowing Ohm's law, which is part of becoming familiar with in this lab, I have to see how much in the range am I going to measure, and well, 3.24 volts divided by 1000 ohms is roughly 3 milliamps, 0.003 amps, or 3 milliamps. So that's what I'm going to put it on, about 20 milliamps. Here's my range, and then I'm going to put it in here. For the amps, for the current, I have to measure it in series, and that means I have to break the circuit open momentarily, and that was not meant to be. That resistor is supposed to stay there. Okay, let's do this again. So for it being part of the circuit, I have to interrupt the circuit in one place, and that's where I put my ammeter in. So here's where I'm going to measure in between. Again, I disregard the negative. It simply means that I should turn my leads around, but the number here is the same. So 3.38 milliamps, 3.39 milliamps is what I got. And that's as far as the circuit goes, and as far as measuring inside the circuit goes. I will later have another recording where I show what to do with these data.
This is for having a resistor with a battery, and I didn't use 390 ohms. I used 1000 ohms because, again, I don't want to take work away from students. So I'm going to cross this one here out. This is just going to be on my answer sheet here for my examples, and I better paste the ohm in here. So according to the color code, I should have used 1000 ohms, and I measured 992 ohms. Better not forget the unit. I measured a voltage of 3.24 volts. I measured a current of 3.39 milliamps. and then I compute the resistance according to Ohm's law, and that of course is voltage divided by current. And so that would be 3.24 divided by 0.00339, because it was 3.39 milliamps, so 0.00339 amps, and I come up with 956 ohms. Seems to be a little bit off, so the overlap between this number here and the measured number and the number given by the color code is not totally on, but still within those 5% that the gold indicates that the tolerance should be. The computed power is power equals voltage times current. So that would be actually 3.24 times 0.00339, and I come up with I can't see the number myself, 0.0110, I guess, rounded, and that would be in watts. Okay, for this one here, how is resistance measured? Well, as you recall from the video that I showed, you measure resistance in parallel to the resistor from the outside with no battery attached. How is the voltage measured? Well, also in parallel from the outside across the resistor with, of course, the battery attached, respectively, the switched on. How is the current measured? Well, wherever you want to measure the current, that's where you break the circuit open, and that's where you put the ammeter right in there and make it part of the circuit.
This is the series circuit, and for that one I've chosen a 100 ohm resistor. It comes with the kit, and there's a switch, and a 150 ohm resistor according to the color code, and a 240 ohm resistor, and a 470 ohm resistor. Again, that's according to the color code. And then I measure the individual resistances. I could do that right now. I don't have to, because I shouldn't have a closed circuit anyway. 99 ohms, 149 ohms, 246 ohms, and 473 ohms. And before I forget those numbers, 473, 149, in the meantime I forgot this one here, 246 ohms. Of course, that's within the tolerance that these resistors have inherent to them. Okay, I could have measured here also the resistance as long as the switch is in the off position. The total resistance I measure from the beginning of the first resistor to the end of the last resistor, and that comes out to 967 ohms. And then I measure the voltages. So I turn this one to volts. Of course, I have to turn this on. Just double checking the battery on the voltage. The voltage on the battery, 3.01 volts. And now the individual ones, 0.31, 0.46, and again I disregard the negative, that's just turning the leads around. So 0.76 and 1.47, 0.76. And there's already one thing that I can see, that the higher the resistance is, the higher is the voltage as well. And then I measure the total voltage again. It's starting from the first resistor to the last resistor, and the total voltage comes out to 3.01. That's the measured voltage. And then later on I also have to compute it from the individual voltages, and I can already see that I'm within 0.01 volts on that one. Okay, measuring the currents. For the current, again, I have to take out one element at a time and measure the current. So I'm going to take the switch out, and of course I turn this one here to electrical current. In this case, again, I'm kind of estimating I'm going to have about milliamps here, a few milliamps. So this one here is the current that goes to the first resistor, which is 3.10 milliamps. Take this one out. Current through the second resistor, 3.10 milliamps. Again, disregard the negative, that's just turning the leads around. 3.10 milliamps. How much is it? 3.09 milliamps. Again, that's within tolerance. Oh, that's because the last one came off a little bit at times. 3.10 milliamps. But even if it was a little bit off, that's within the tolerance of the resistor as well as the multimeter that I use. So 3.11. Actually, the last one here could be considered the total current, but I can see already that whatever I get here, it's the same number. That means that the current flowing through any resistance in a series circuit is the same current. Which makes sense, because the current has to stay the same as it goes through here. Just like you have a river, it's always the same amount of water flowing down the river no matter where you are, because otherwise, if it isn't, then you would have a dam of water, or you would have just a trickle of water at the time, and that's just not possible for a river, and the same thing for an electrical circuit. Okay, I think all the rest that I have on here for the series circuit would be calculated in a recording that I'm going to do later.
This is 4 resistors in series. And again, I'm not using the same values that you find on your lab sheets, because I don't want to take work away, but I use these resistors. And I better not forget that each of these numbers has a unit. These are all the numbers that were measured. And if we added these up here, the measured resistance, we in fact would come up with something relatively close. Let's see, 99 plus 149 plus 246 plus 473 comes out to 967. And remember, measuring this one here, this one actually is a computed result. I should also allow a box for this one little here, so that's what I should write down here, equals 967 ohms. According to the color code, it would be 250 plus 240 is 490 plus 470 is 960 ohms, and that seems to be really close to a 967 here. Okay, measured voltage. This is where the measurements. These here is the total measured voltage, and if we add up these numbers here, 0.31 plus 0.46, it's 0.77, plus this one here is 1.53, plus this one here is 3.00 volts. And then better make sure that I put the volts on here everywhere. Okay, this was the measured current. And then the computed resistance, well, it's according to Ohm's law again. So R equals V over I. And for that one, I'm going to use the measured results, of course. So divide these by each other. So this is going to be 0.31 divided by 0.00310 amps, and I come up with exactly 100 ohms. And then I do the next one, 148, and the next one, and the fourth one, and then I do the total as well. And those are going to be the numbers that I write in here. So that was 100 ohms. 148, 245, and 474, and 971. And as we can see, these numbers are all really close to what they should be. And then the computed power. Power equals voltage times current. So it's going to be 0.31 times 0.0031 for the power, and so on. Okay, that's the last result. Actually, that's the total. I'm going to do this on the side here, and then you can see what the results are. Okay, so that was the 0.00933, and this one I just calculated to 0.00096, and that's in watts. And this one is in watts, and this one I calculated to 143 watts. And then I noticed that actually I had accidentally multiplied here by, I divided by 3.10 for the resistance. So by dividing by 3.11 actually comes out to 968 ohms, which is even closer to what I had measured. Okay, the last two results here. Okay. How do resistances add in a series circuit? Well, I kind of give it away with this one here, and of course with the numbers that we have seen here. In the series circuit, the resistors simply add. We can see that on these numbers here. We can see it on these numbers here, and we can see it when we compare these numbers. How do the individual, oops, that's actually off the screen, sorry about that. How do the individual voltages add in a series circuit? Well, you just add the voltages and you come up with the total respectively. It's off by a little measurement error. Oh, that reminds me, again, I have to fill in a little box here where I will put in the computed one from the measured resistances. Okay, how do the individual currents compare in a series circuit? Well, they're all the same, going through any of the resistors.
This is for resistors in parallel, and the resistors I chose do actually not include the 100 ohm resistor, which means that as I use these here, and I only have 3 of these, I have to put them in parallel, just like that, for example. So just click 2 of these resistors in here. There. And here we go. And they're actually in parallel. If I actually wanted to click one in there that would be in series, well, I would hook it up into these 2 springs here. But that's just on the side. Anyway, so now I got 4 resistors here, and I want to make sure that I use the right ones. So I'm just going to measure. I actually unhooked this here for the moment so that I can determine what resistance I have here. 149, so that's my 150 ohm resistor. And actually, I have to measure it anyway, so I'm going to type it in here. 149 should be 150 according to the color code. The other one, according to color code, should be 240. And let's see, I got 242. I hope my arm is not in front of that. And then the other one I have here is 246. So those are 2 that should be the same, but of course at 240, but within tolerance they're just slightly off. And then the 4th resistor that I have is 473. According to color code, it should be 470, but here it's 473. Okay, so those are the 4 resistors. Okay, then I'm going to put them all in parallel. There is the switch. And there we go. Okay. Now the switch is in the off position. Now I have them in parallel with each other. Notice I could have connected them here as well, but there's a certain reason for doing it over here and bridging it over to this particular lead. And that is when I measure the currents later, it's going to be much easier the way I have it arranged. Oh, I have to connect my single resistor from earlier. Put it into the spring, hopefully. Okay, great. Now, alright, both disconnected. There's one. And maybe the other one. Oops. Huh. Sorry. Sorry that I do this here. Show me what I mean. Okay, now I hopefully got it. There we go. Okay, the camera turned off on me, so now I don't know how much it recorded. In the meantime, I was able to hook them up here, and my switch is in the off position, so I just go as usual for the resistance across here, and I measure a total resistance of 59 ohms. And when I look at any of the other numbers, I possibly could not come up with 59 ohms. Perhaps the only thing I can notice is that the 59 ohms for the total resistance is less than any one of the other resistances. Okay, let's turn the switch on and measure the voltages. Voltage across the first resistor. Change those volts here. Voltage across the first one, 2.92 volts, and disregard the negative. Next one, 2.91 volts. Either way, 2.91. And across the third and the fourth, and I could take these singly apart here, but it really seems like they're all the same here, 2.91 or 2.92 volts. And then it says the total voltage would be, well, anywhere here, also 2.91 or 2.92 volts. Yep, there you go. I'll write down 2.91 volts for the total. So, with that one, I already conclude that the voltage across any resistor is the same in parallel, no matter where it is, which makes sense because they're all connected on the same side here to the same lead to the same side of the battery, so the voltage here should be the same. Okay, for the current, so I'm gonna turn this over here. In this case, actually, notice that the total resistance was only 60 ohms, so I may want to put it a notch higher to 200 milliamps because it may just measure more than 20 milliamps this time around. I'm going to start out measuring the total current, which is I disconnect this one, and of course put the ammeter at this point here inside the circuit, so that's 48.9 milliamps. And that was the total current. For the 470 ohm resistor, comes out to 6.1 milliamps. For the one of the 240 ohm resistors, it comes out to 11.8 milliamps. Again, we disregard the negative. We connect, and now I have to take it out here anyway, and have to measure this one here. This is the other 240 ohm resistor, and I come out with 12.0 milliamps, which is virtually the same as 11.8 because the other one was the same kind of resistor, just with intolerance a little bit off. Okay, and now I have to see, because I had already trouble up, they're totally disconnected now. Because now it's the other one that I want to measure. Okay, now I have them totally disconnected again. This could be the same kind of problem like before. One, and this time around, fortunately, I only need one. There we go. Okay, 240 ohm resistor is connected, and now I go in here to measure the 150 ohm resistor, which gives me 19.4 milliamps, and with that I can also conclude something, and that is that the resistor with the least amount of resistance has the largest current going through. So that saying about that electric current takes the path of least resistance is indeed true. The other numbers that I see on here are definitely computations, so the measurements for the parallel here are done.
This is for the resistors in parallel. And these are the measured results. And again, I better copy the unit in here. So these were the measured results, and then this one here is the total resistance. And if we look at that number and compare it to the other numbers, then we can see that there is really no way we could think about how we could come up with this number just by looking at these other numbers. Okay, let's see what else happens. Here's the measured voltage. So the voltage across all the resistors is the same when they're in parallel. And here's the measured current. And then here's the total current. And again, I may want to actually paste this in here. And this is voltage. Okay. Again, Ohm's law. Divide this number by that number. The voltage divided by the current. So 2.91 divided by 0.0194 amps. 2.91 divided by 12 milliamps. 2.91 divided by 11.8 milliamps. Oops, now I don't need the period anymore because I already have it in amps. And divided by 0.061 amps, and then I'm going to jot down the numbers. 150 ohms, really close. 243, rounded, really close. 247, really close. 477, pretty close. I mean, even that is within 1%. And then the final one is going to be let's see what oops, okay, I guess I'll start over. Divided by 0.0489 amps, and I come up with a rounded 60 milliamps. Oh, whoops, a rounded 60 ohms, which is basically the same number that I measured over here. Oh, here I forgot one thing, which is add up these numbers here. It's going to be, let's see, 0.4, 0.8, 0.1, that's 0.3, carry 1, that's 20, 32, 43, 49, 49.3 milliamps is the computed one, and again that is within measurement error that these two are not exactly the same but pretty close. The computed power again is voltage times current, so 2.91 times 19.4 and so on. 90.4, whoops, it's not true, times 0.019 194, 2.91 times 0.0120, and so on. And the total is going to be 2.91 times point, whoops, not there, my calculator. Oops, 0.142 watts is the total power. Okay, in parallel, how do resistance add in parallel? And I get to that in just a moment. Compute the total resistance and so on. I get to in just a moment as well. How do individual currents add in a parallel circuit? Well, they add straightforward. Just add them and you come up with the total current, as you can see here when you compare these two numbers. How do the individual voltages compare in a parallel circuit? Well, they are all the same across each of the resistors that are in parallel. And how does the total power of several resistors in parallel compare to a total power of several resistors in series? Well, here we have a total power of 0.142 watts, and here we had a total power for the series of 0.00933 watts, so quite a bit less in series than what it is in parallel, or quite a bit more in parallel than what it is in series. In fact, in a parallel circuit, you get the total power to everything you put in the circuit, all the appliances, in this case all the resistors. In series, you get only a little bit of the power to them. The total current is relatively small, as we can see, and they all have to share the voltage, while here they all have the nominal voltage from the battery. By the way, the reason that this one here is 3.01 at 2.91 instead of the former 3.01 is because I had left the circuit on for a few hours and then came back later and noticed, oh, okay, it drained the battery just a little bit. And in any case, the total current is relatively high when you put them in parallel, which also means that when you have appliances in parallel, such as in your house, that it increases the current, and therefore you need circuit breakers, because at some point the total current could potentially exceed the current for which the wires are rated, and all of a sudden you have an electrical fire. So in a household, everything is in parallel, but you have to pay attention to that the current may be just too high. Why are they not in series? Well, you notice that earlier, as soon as I turn a switch off or take a resistor out, nothing is working in a series circuit anymore, so you cannot put appliances really in series. You have to put them in parallel. In any case, let's answer these questions here. How do resistances add in a parallel circuit? And that's what the footnote is about. So I'm just going to see that I copy this footnote. There we go. And actually, I will put that to the next one. There we go. Add the reciprocals, and then for this one here I have to put in the numbers. Well, that one, when you look at these numbers here, as I said several times already, that you just wouldn't be able to come up with 59 unless you do know how to do it. In this case, I have to give it away. You can't just look at the numbers. I have to give the correct formula away. So let's see what we come up with. This one here is 149 ohms. And I need those ohms here. There we go. Fortunately, due to the edit, this is taking quite some time. And then, of course, I don't have a fifth resistor. So I add the reciprocals of these numbers. I'm going to move this a little bit up here, so I have both the numbers as well as being able to use the calculator. So 1 divided by 149 plus 1 divided by 242 plus 1 divided by 246 plus 1 divided by 473. Enter 0.0170 is the result. 0.0170. Notice that the unit is in the denominator though, so I'm going to do this ohms to the -1, because that indicates that it's in the denominator. And when I look at that, well, that's not what this number is, not the same as this number here or that number here. Well, because the original total resistance or equivalent resistance here on the left hand side is in the denominator itself, what I have to do is I have to invert that again. So invert again, and 1 divided by 0.170, and at this instance I'm allowed to write ohms because that will be in ohms. So 1 divided by that result is 58.75 or 59 ohms rounded. So 59 ohms, which compares nicely to what was measured, what was calculated over here from these two measurements. So that's how resistances are added in parallel as their reciprocals. There's a recording for the circuit labs, and one applet that is really nice is the PhET, Physics Educational Technology. So search for that on the internet and then go to the one on circuits. And let's see, I should have it here very quickly. Let's do DC only. And there it is. Okay, not everything shows here, so I'm gonna see how I do that. I want to just grab a light bulb, grab a battery, grab a switch perhaps. I'm gonna turn this way, and a wire, and another wire, and again, and one more. Oops. Be a little bit careful here because it kind of jumps around here if you accidentally click it on the wrong thing here, then it's kind of tough to get away from it. See, it always wants to move there. So if you accidentally get it there, well, that would be actually a short circuit here. And you could see that that produces some fire in the battery. Anyway, so now I got to connect correctly, and I close the switch, and it glows quite brightly. I'm going to put a second battery here in here. And basically, I'm just playing around with this here to show you that this is how the applet works. There we go, and close it, and there it is, quite brightly. Okay, now I'm going to put one in parallel, I wanted to say, but I think I wanted to measure something. I'm trying to grab the switch. There it is. So I'm going to put actually another light bulb in here. And there. I'm using too many wires, but I'm just not sure if I need to break it up here at some point, so that's why I use so many. Okay, and then I close the switch again. And it's actually equally bright as it was before. Notice that if I break that off here somewhere, I'm trying to pull it away there, that this is the same brightness no matter what. So in parallel, it actually gives the same brightness for both lamps, which of course means that these two lamps must be using twice as much power. So one of the answers to the questions on the lab would be where it says connect 3 light bulbs in parallel. Sure, I'll connect a third one here. It's probably going to be slightly out of the picture. So there we go. So they're all in parallel. And it says what happens to the brightness of each light bulb when they're connected in parallel, and the brightness stays the same. They're equally bright as if there was only one of them in that circuit. Measure the total current. So that's what I'm going to do. I'm going to open this one here, and if I want to measure the total current, I have to interrupt it in the place where I want to measure it. So here, that's where I would measure the current. There's the ammeter. It just popped up here. Okay, it looks like a little bit out of the picture. There we go. Oh, yep. Now I need another wire. And let's see if we can actually read that. Oops. Then I can't read it. Split the junction. Still cannot read it. Where did I put it so that I actually can read it? Try it this way. There we go. Connect it. Close the switch. And it says 5.4 amps is what I measure here. For how long would the light bulbs glow? And for that, I have to look at the footnote, and it says the capacity of one regular alkaline AA battery is about so and so much, and a C battery so and so much, and so on. So I would have to see what kind of battery am I actually using. And I know that these kind of look like a AA battery, but they're not. This is a 9-volt battery. So it says here that a 9-volt battery got only 0.5 amp hours. So I take the 0.5 amp hours. Of course, I have 2 of these here, which is 1 amp hour, and I divide that by 5.4 amps, and I come up with approximately 0.2 hours, which is about 12 minutes or so. And I think we can see that these light bulbs are so bright that if I have that large of a current and I put two batteries in here. Oh, I take that back because I have two batteries. I actually have twice. No, that's right. One amp hour divided by 5.4 amps, and that comes out to 0.2 hours, which is 12 minutes, and then the batteries are gone. Anyway, this whole thing was just to show you how to set up a circuit with this applet. This is an example for drawing a circuit using the circuitlab.com editor. And so let's see, I'm going to start out here with a battery. I'm just going to call it battery, and maybe I have two AA batteries, and that would give me a total of 3 volts. Okay, then I'm going to take 3 light bulbs. So as I'm scrolling down here, it took me a while earlier to actually see them. There they are. Okay, there, another one. Actually, before I take this one here, a little bit too much information here, so maybe I call this lamp 1, and I don't need this here. There we go. Okay, and then maybe, let's see, okay, I just copied and pasted it, and I think I want to draw the one that is in parallel. So I suppose lamp 2 here. There we go. I really don't have to relabel it that much. There we go. Even if you left that out, that would be okay. Let's see. Then I'm going to take a lead to find that one. Okay, I think I remember. I just grab this one here and draw it over there, and there it connects. And then, as I point out in my lab manual, if you actually build it, you may want to make sure, and I'm just grabbing this here and pulling it over, you may want to leave some more space here and then connect with single leads over here, because you need to have some space in between here to measure the current. Maybe I'm going to put in one more thing here. Let's see. There we go. Oh yeah, I wanted to put a switch there. Let's see, where did it go? I saw it earlier. There it is. There we go. So there's my switch. Double click on that. There we go. In this case, it's in the open position. You can draw it like that, or you can draw it in the closed position. Let's see how it looks like. Oh, that looks cool too. Alright, and then I might as well put an ammeter in here. So for an ammeter, what I would have to do is I would have to break the circuit right here, and that's where I would have to put it in. So now I have to find it. Just a little bit off the screen, there it is. And that's where it would go, and then I would measure the amps right there. Okay, and that's how you draw a circuit with the circuitlab.com, and then you would have to copy it from here and paste it into the lab report. Okay, and now I'm going to draw a parallel circuit with resistors. So I'm going to take the lamps out. There we go, and the resistors are, oh, I think I just saw it. Nope, it's not it. Let's see, there they are. Okay, so put one here. Already have an ammeter there. Put one there. Put one there, and I guess I said I would use 4 resistors. So one more, and then I connect lead here and there, and if I wanted to switch, oh, I have to connect up here. If I wanted to switch my ammeter, I'll do it like this. There we go. And if I wanted to switch these here, whatever values I have, I think 220, 270. They don't need to be in that order. The circuit would work either way, this parallel circuit or a series circuit, no matter what order you put them in, but I might as well put them in the correct order because then it's easier to keep track of all the values. And there you go.